All right, in this video, we're going to just do a quick little review of Cartesian vectors, which covers chapter 6 in the book, but I'm also going to be using this to take a look at a couple of items that can be used with chapter 6 word problems and problem solving. Okay, now Cartesian vectors, just as a reminder, the word Cartesian implies on a Cartesian plane or something that looks like a Cartesian plane. So it could be a directional system like north, south, east, and west, because it has the same setup as a Cartesian plane. Here we've got a simple vector going from A to B on the Cartesian plane. And we're going to take a look at the component form and how that works. So just to quickly review that. So component form is kind of just a shortcut in a way to talk about how you would move using vectors. So to go from A to B, all right, so the logic behind this is to basically say, well, oops, gotta get the right bracketed notation. Okay, so the logic is basically how many units to move horizontally and how many units vertically to go from A to B. So using the Cartesian plane, it's very straightforward. If we're going from a situation that we are looking at starting at point A, which has a horizontal x value of 4, and I want to go to a horizontal point B, 6, I must move 2 units to the right. So 2 units to the right would imply a positive value, right? So the horizontal component for vector AB is 2, and then the vertical component in a similar fashion is vertically going from this level of 2 for A to 8. So that gives us 6. Now the mathematical way of actually calculating that, and that was part of the formula, was to utilize the values that were given in the question itself. So in this case, it's not really much of a question. It's more a matter of just taking a look at the ordered pairs that are given to you. And in this regard, we're looking at this calculation coming from taking the ordered pairs in a very specific order. So notice it's AB. So to get a value of 2, it's how far are we traveling? So think of it as a distance from the ending point, in this case, a horizontal value of 6, taking away 4. So that will give us the 2. So this is a way of calculating the horizontal and vertical components without using just simple logic. Okay, so you can use any technique you want. Similarly for the y, you take the y value from the second point, which in this case is B, and you would subtract the y value from A. And so the second part is how you calculate these values. The first method that I just talked about, getting the 2 and 6, is simple logic. So you can use any technique you wish to come up with this. And just to briefly go through as well, if you had to talk about the opposite vector of AB, which is BA. Oops. So again, from a calculating point of view, I would do exactly the same thing. So I'd use the the horizontal component of the x coordinate of the A, take away the x coordinate from the B, and then similarly the y coordinate from the A, take away the y coordinate of the B. All right, now let's see what this produces. So mathematically, we can get 4 take away 6 is -2. And then we'll take a look at the meaning behind this. 2 take away 8 is -6. Okay, so what this essentially means is that to go from point B to A, and then from up here down to here, opposite vector now, I need to travel -2 horizontally, which makes sense, and then -6 vertically. So that's why these labelings, vertical and horizontal components, whoops, are extremely vital when you're taking a look at these types of things. Okay, So that's just a quick little review of component form. Another quick little review of unit vector form. Now, unit vector form is just a different method, again, on how to talk about vectors. And they rely on you looking at these simple vectors that are kind of like preset vectors for you to use in terms of stepping. So I and j are the little vectors. So they always point in the positive directions, these I and j. So we're going to take a look at writing this vector two different ways, in component form and using unit vector form to show you how this works. So in component form, since we're starting at A and ending at B, we have vector AB. And again, just from a logical point of view, I'm going from a horizontal value of 2 to a horizontal value of 8. So that gives me a horizontal component of 6 to the right. And I'm going from a vertical component of 6 for A to 2. Oops. So from 6 to 2, I have to go down 4. So that's -4. So again, you can calculate these values by getting the y-x coordinate from B, 8, take away the x coordinate from A, which is 2. And then the y coordinate from B, 2, take away 6, which is -4. So essentially, to go from A to B, I need to go 6 to the right, 4 down. Okay. Now, with unit vector form, it's a pretty simple process. You essentially take a look at the values that you have in the component form and utilize them with your matching them up with I and j. Now, I and j have to point always in the positive direction. So if I have to use travel 6 units to horizontally speaking to get from A to B, then I'm going to need 6 of these. Oops, you know what I just realized is I've got I and j mixed up. Terribly sorry about that. So I is along the x, is the horizontal, and j is the vertical. Sorry about that. Okay, so to travel 6 units horizontally speaking, I'm going to need to travel the equivalent of 6 little I vectors. So that then says I can rewrite the component form this way. So I need to travel 6 of these. And let's see if we can just do this real quick as a demonstration. So I need 1, 2, 3, 4, 5, and 6. Not perfect, but hopefully you get the idea. And then I have to travel down 4 units to get to B. Now, down 4 is the opposite of J. So watch what happens. If I try to do this, I'm actually going in the opposite direction. So I need to kind of swing this around and go in the opposite direction, but I need 4 of those. Now, these are known as unit vectors, and the reason why we call them unit vectors is because their magnitude is 1. So hopefully, without having to draw them all out, I'm sure you can understand that we're going to be traveling 4. We're going to need 4 of those j vectors, but in the opposite direction of what j always points to. Okay, so that's unit vector form. And that goes along with multiplication, scalar values, multiplying with vector values as well. Right, so just a quick little review there. Okay, now Cartesian vectors, just to review this as well in component form. So again, we have something on a Cartesian plane, and now the difference between this type of setup is that you'll notice that I'm not given coordinates for point A. So if I wanted to try and discuss a vector from O to A, so if I wanted to represent this vector now using component form, so let's just get this set up here. So if I'm looking at OA as a vector, I'm trying to figure out what am I going to use as the different components. I don't have coordinates for x and y. I've got an angle, 45 degrees. Now that angle could be anything, But this is where you have to rely on previous trig knowledge to try and understand what's going on here. So I'm going to hopefully make some sense out of this, and then we can fill in this vector notation for component form. Okay, so here's how this works. Now, back in trigonometry, what you should have realized, this is a typical setup for your trigonometry based on previous knowledge courses. Okay, so this is the x-coordinate, your y-coordinate. R stands for the radius. If you recall, there's like a circle that you can rotate that arm around. And this arm, very much like a vector, right? So that radius there, and even though we're talking about it in terms of a vector. So if I wanted to determine what x was, because it would be nice to have that x coordinate, because then I can come up with a vector. I already know that the O is the origin, which is 0, 0. So I've got coordinates there, but I don't have coordinates for x and y. If I can find x, then I can make my life a lot simpler. So here's what I'm going to do. So I'm just going to grab a copy of this, and hopefully this works out for me. Let's see if it does. So if I wanted to solve for x, it's as simple as multiplying both sides by that there. And I've got x. So multiplying both sides by r, I now have a way of writing x. It's r cos 45. Okay, because the cosine of 45 is x over r, as you're familiar with. Now, keep in mind, r is the length of that measurement. I know we're talking about vectors, but in terms of vectors, that would be the magnitude of that vector. So that magnitude could be a speed, it could be a force, or it could be something you need to calculate. Okay, it could be a tension, you've seen in some other examples, right? And then the same thing can apply to sine. So without having to copy and paste, I'll just multiply both sides by r, and then get rid of that little division sign. We don't need that. So now we've got a way of writing the y value. So vector OA now becomes, now if I use exactly the same technique as we did before with components. So if I take the y value, or sorry, the x value from my ending point, so if I'm going from O to A, my ending point is going to be my x, okay? Take away 0. And then my vertical component will be y take away 0. As mentioned previously, this is not very helpful, is it, in terms of working with this piece of information, because generally with word problems, there should be a way to find the magnitude of different vectors, and that's what the OR is all about. So if I can now replace, now minus 0 is not really going to do anything for me, because that's just going to simplify to just x in this particular case. So now I'm going to replace the x with r, and then cos 45. And of course, it'll be degrees in this particular case. Let's see if we can make it a little fancier. There we go. And then I'm going to replace the y, since this is just y take away nothing, with r sine 45. And once again, it is degrees. So now I have a way of discussing in a much more usable manner component form with Cartesian values. Okay, and that's using the angles. So if you're given angles, so, and this is when you're creating diagrams that are helpful and have angles in them, and you have all these informations with word problems. So what you need to know is that R would represent some kind of magnitude of the vector. Okay, so that's how you use it in vector form. So hopefully that clarifies a little bit in terms of how this works. So we are going to take a look at a word problem. Now this word problem, as I've kind of highlighted here, it's coming from 6.4 actually. So even though this concept of component form is in chapter 7, I think many students will benefit from using component form to solve some problems. So we're going to take a look at this one. And there's a little video link that I'm going to add to this one that you can take a look at as well. To kind of clarify some of these things. Okay, so here's a typical example of solving problems with components. But one of the most important aspects is this equation up here. You have to set up some kind of addition question or vector equation, as we call it, that makes sense for the problem. So I'm going to talk about this because if you don't set this up properly, then the rest of the math really doesn't matter much. So you have an airplane that is flying at an air speed, so in the air, 500 kilometers per hour, and that gives you a heading, okay, so a direction. So you have magnitude given to you here. It's the magnitude of the vector, and this is the direction of the vector for the plane. Okay, so that's what I'm referring to here. Okay, so that's one aspect. Then you have a 150 kilometer per hour wind that is blowing from a bearing of 120. So there's the information for vector W, which I'm referring to as wind. You have a magnitude and you have direction. You're asked to find the ground velocity. Now, just to explain ground velocity again, it's essentially, this may not be the best analogy, but if you were a superhero and you're able to fly or run on the ground directly beneath the aircraft, you would be tracing out a path on the ground, like on a map, of where the plane is flying. Now, you have to think of this logically. The movement of the aircraft is dependent on, in a weird way, its speedometer. Okay, so I know that's kind of a strange way of saying it, but that's one way of thinking of it, followed by what is acting on it to move it. So if you've ever been in a windstorm before, which I'm sure most of you have, you've been walking on the sidewalk, you know that wind can push you in different directions. So you have to counteract that movement of the wind to get you to stay on the sidewalk. Otherwise, the wind would push you off the sidewalk and push you onto the road and all sorts of places. So the same idea works with aircraft. So they have to point the aircraft in a certain direction. They have an initial speed, but if you ever wondered why sometimes it's faster to travel to Europe than coming back, it's something called a jet stream, and that's a lot of wind, right? So in this particular case, what you have to understand is that the ground speed is, or the ground velocity in this case, is trying to tell you what is the net reaction of the plane having engines that are trying to get it to move 500 kilometers per hour, assuming nothing was affecting it in any way. But then there's wind that's going to affect it and make it move in a different direction, okay, or alter it in some way. So those two combined efforts, forces, whatever you want to refer to it as, combined in addition. So when you put these two together in addition, that gives you the net ground velocity or ground velocity vector. And again, think of it as running underneath the aircraft, and that would give you the resulting value. Okay, so this is a very powerful tool, especially if you get questions where you're given information regarding the ground velocity or ground speed. So if you're given the ground speed and you're asked to find the plane's velocity, you can still use this equation, but think of this like a grade 9 technique. How would you find P if you had information that allowed you to complete G and W? Well, exactly right. You would isolate for P, and it would be G minus W, so you're subtracting vectors, right? So this is a very powerful technique and can be very useful instead of drawing triangles and trying to use sine law and cosine law. So it's very powerful and probably very useful for most of you to try and get through. And it can be used for chapter 6 problems, no problem, no issue whatsoever using that. So let's take a look at how you'd set this up. So you're given information regarding the plane. So that's what I have here. So the plane is traveling on a heading of 040. Now remember, that's a bearing. So bearings start at north and then go in that direction. So it's 40 degrees, what we call in a clockwise direction from north. So that gives us an angle of 50 degrees down here. Now, why is that important? That's important because if you remember earlier, the angle that we need to use in this component form, if I didn't make it clear earlier, must be from the positive x-axis. Well, at least the way I would suggest doing it anyways. Okay, so always stick with that, and then you won't have to worry about anything else, because there are some other techniques you'll see, but I think that's the safest approach. So I'm trying to come up with a representation in component form for vector P. I have the angle, so this would be R, and then cosine of 50 for the x, and r sine of 50 for the y component. Okay, so the r that we talked about in the previous example here, like I said, it's the magnitude of the vector. All right, so in this word problem, the magnitude is your speed. All right, so that's where these two come into play. All right, so what else are you given? You are given information regarding the wind. And the wind has a particular magnitude of 150, but its direction, if you take a look up at the top of the question, it says a bearing of 120. So again, there's 120 in the diagram. Okay, and now you might be wondering why this is using cosine of 150. So let's take a look at why 150 is being used, because it doesn't seem to be evident in the diagram. I thought we were supposed to measure angles from the positive direction of the x-axis, which is here. So if we measure that angle, well, we got a bit of a weird situation. So there's the bearing of 120. There's the vector, but let's take a look at what's actually going on here. There is a very key important information right here, blowing from a bearing of 120. So that means the wind is coming from this direction, but actually blowing that way. Okay, so that's extremely important, because now what we have to do is consider a vector that is parallel to this, but actually going that way. Okay, so the wind is actually blowing, instead of what we would say southeast, it's actually blowing northwest. Okay, so it's from a bearing of 120, so you can start with that, but the actual wind is going in the direction of the red that I'm indicating here. So the angle that we're looking at using for our component forms from here to here, that's where the 150 is coming into play. So just using some basic angle measurements and trigonometry, if this is 120, that's 60, so this must be 30 up at the top. Sorry, this is 30 here. And just a moment for 1 sec. So up in here would be 60 degrees to match that. Now we don't want the whole 120, we got 60 plus the 90. So we get the 90 plus the little 60, 150 degrees. Okay, so just to be clear again, we have this little angle in here that is 30 degrees. Just gonna make that very small. So that would be 60 degrees up there. All right, and that leaves us with a measurement that we need to calculate from here to here. So again, if we have a 90 plus a 60 is the 150. Okay, so what does that allow us to do now? Well, we are asked to find the ground velocity. Ground velocity means I need the magnitude and the direction for the plane using the addition of these two vectors. So it's as simple as taking these two vectors and adding the horizontal component and adding the vertical components together. This is calculator work, folks. That's all it is. Simple and easy calculator work. All right, it's a little tedious, but other than that, it's very logical and it'll work out for most questions. So sometimes it'll take more writing and more organizing to deal with components than it would for using sine and cosine law, but this is completely up to you. Okay, now what you have to understand though is this component form gives you the components of the vectors. It doesn't give you the magnitude or the direction. You have to determine that yourself. So think of this component form as almost like on a Cartesian plane. So you would have to travel 191.49 units horizontally and then 458 vertically. So that's what I'm diagramming here on the Cartesian plane. Approximately 191 to the right and 458 up. So there's your ground velocity vector. Does that give me a magnitude of the actual diagonal line in the diagram? No, it doesn't. How do we find that magnitude? Well, this is your grade 10 math. This is just Pythagorean theorem, all right, for triangles. So you get the magnitude of g, which is going to help with your velocity because you need the magnitude in the direction using Pythagorean theorem. So it's pretty straightforward. To get theta, you have a right angle triangle and you have the opposite and adjacent sides. So guess what? You're going to need a little bit of trigonometry, tan inverse, get you the angle in degrees. And then how you come up with the conclusion is really up to you. So you know that the angle between easterly direction and northerly direction. So again, what you have to keep in mind is the system that you're using here does have a north, south, east, west technique. So this is east, oops, and this would be north. Okay, so the plane, the ground velocity of the plane can be talked about in terms of north and east, which I have down here below. So east, 67.3 degrees north, but you may see things online or solutions in your textbook where they use bearings. Now, why would they use bearings instead of the north, south, east, west system? Because the textbook question itself had bearings in it as the initial measurement angles. Doesn't really matter though. So where's the 22,022 coming from? You would have to actually calculate this little angle in here because that's what the bearing is. It's between north and the vector. And if theta is 67.3, and that remaining angle, since it's a 90 degree, and there would be approximately 22 degrees, which is close enough. All right, so about as accurate as you can get. So the velocity includes the magnitude and the direction. So again, it takes a little bit more writing, but it's a little bit more logical for some of you to maybe get through the word problems, regardless of whether you're dealing with chapter 7 or chapter 6 techniques.